Our second talk this afternoon is by Professor Ron Addie, and it's titled Snapshot Simulation, an important sampling technique for traffic with heavy-tailed flows.
Thanks, Paul. And thank you also to the organisers for the pleasure of speaking at this meeting. It's great to be able to speak to an intelligent and interested audience, some of whom are asleep, and some of whom didn't sort of pop out to see the World Cup. This work is joint with my colleague Moshe Zuckerman and Derek Pao and Eric Wong and Zhongche Chen, who are at the City University of Hong Kong. And so I'm going to talk about how to simulate systems which have heavy-tailed flows. And I'm going to talk about a different challenge, the problem of heavy-tailed flows from a different point of view. My interest in systems with heavy-tailed flows goes back quite a way, at least 10 years. And I sort of pretty quickly came across this problem that when you have heavy-tailed flows, it takes a long time to explore the state space. And so the normal approach of using importance sampling is really not going to solve that problem, because you're just going to have to take a very, very long time to move around the state space, and therefore to discover the sort of statistics that you want to look at. So, and at first I attempted to struggle with that, and I thought it was really a bit hard, but it sort of just worked away at my thinking, and so I came up with this technique which I call snapshot simulation. Okay, so a little bit of background. I'm talking about flows here, which is not quite the same as jobs. If you think about networks, we have things like a web download, or a DVD download, or a download of an operating system, or a little bit of internet banking. And they obviously vary enormously in size. And to give an idea, I mean, a lot of people are carrying around smartphones these days. A colleague of mine went overseas with a new iPhone, and before he went, he said, look, to his operator, Telstra, please turn off the data because I'm a bit worried about the cost. And they said, fine. So he went overseas, and the data still seemed to be working, but it didn't worry him too much. And he came back, and he had a bill for $2,000. And he was a bit puzzled about this. He rang them up, and they said, oh, yes, sorry, we forgot. But he had to pay the $2,000. And a friend of his had a similar experience. He watched one movie, and it cost him $10,000. Australian dollars, that is. Now, that's because we're just unfamiliar with how large some of the demands we put on resources are. And that's that's a heavy-tailed flow. And at 25 megabytes for $1, an Australian dollar, it adds up pretty quickly. And that's actually not unusual all over the world. That's basically pretty much the rate. So using a lot of data on your iPhone is quite expensive. So these here represent the flows, all of these lines. And the majority of them are very small, but every now and again you get a very large one. An intuition for it is that most bytes are in large flows, but most flows are small. Now, I'm interested in a whole range of disciplines. The flows could queue, the packets within the flows could queue. Those are two different things, or you could even have a bit of both. Because I spent 20 years working in a networking company, so I'm really interested in the way these things work, and also we're interested in optical networks. So the context is quite broad. I don't want to limit myself to specific queuing systems. All right, now the history of this is my first interest in these Poisson-Pareto models goes back before 2003, but there was a paper published at that time which did not use this snapshot simulation method, but which attempted to simulate these sort of systems. And then in 2007 and 2008, 2009, papers were published which did describe the technique, and you can download those from a website. And then in 2003, a paper was published on Poisson-Pareto models in which simulations were carried out, again not using snapshot simulation. And that model was further looked at in a paper published in 2009. Now, the first solution we came up with, or I came up with, was to just simulate in a variety of different starting points in the state space. But there's an obvious problem with this, and that is that you've got to use an a priori distribution for those starting points, and you really should find out what the right distribution of starting points is. And so that's really a bit inadequate, but it is a start. And here's another way of describing the problem. If you have heavy tails, it takes a very, very long time for the system to warm up. So in a classical simulation, you start here and you declare some point, you're warming up, and then you collect statistics. But the problem is that if you've got very heavy tails, and I do mean very heavy, like gamma equals 1.2, for example, or 1.1, which means that we're getting towards the point where the flows don't actually have a mean, then this problem of warming up is quite severe. So the solution involved this snapshot idea is to have the warm-up period is different for different lengths of flows. So the idea is that suppose we're trying to simulate the 20th century. Well, we might start off in 1900, but we also simulate some events that occurred in, say, 1800. So we might simulate the philosopher Hegel deciding on an approach of conflict. We might simulate Plato back in 500 BC, writing a different version of the Republic, because these are influences which had an effect during the 20th century. And in fact, we couldn't possibly simulate the 20th century unless we took those things into account. So this is the idea here. We have long flows being simulated from potentially the infinite past. So there's no starting point for this simulation. It goes right back to minus infinity. But the short flows are only simulated for the last few seconds. And if you think about that, that actually makes a lot of sense. The short flows have a very, very short influence as well. But the long flows, the really huge ones, have a very, very long influence. So that's the basic idea. So there's a startup boundary, and then there's a statistics collection boundary. And in some cases, we collect statistics only at this moment and use a lot of repetitions. Here's an example of a snapshot. So this is numerical, and these are the flows. So each flow has an arrival time and a duration, or a size. And we can look at that graphically. Unfortunately, the graphic's very poor in quality. That's really silly. I mean, I should have put more effort into the quality of the graphic. These are fantastic graphics. And I've looked at a lot of these. I mean, when they're done properly. The information is great. This is a non-linear scale here. So this is an absolutely enormous flow. And even that one is actually very large because the scale is non-linear. But these ones are quite short. So we can, and the special thing about these snapshots is that each one of them is finite, even although it is potentially infinite in its scope. It goes back to minus infinity, but the total number of flows that are actually considered is finite. So some simulations were done in these papers, and the snapshot simulation was used to confirm the accuracy of analytical models. And at present, what I'm doing with my colleagues at the City University of Hong Kong is looking at optical networks and looking at algorithms for deciding when to start a flow, comparing with analysis, and algorithms for managing optical flow networks. Okay, now a little bit about the maths, although I'll do it all in pictures. Basically, we can observe that inside this space here of where the flows, of which flows we're looking at, the arrival times form a Poisson process. And therefore, if we project onto the y-axis, which is the size axis, then that's also a Poisson process. In fact, if we project onto the time axis, that's also a Poisson process. The conventional simulation is to simulate along the time axis. What we're going to do instead is simulate up the size axis. So, and we will do this repeatedly. So we generate a snapshot by simulating up the size axis, and then simulate it and collect the statistics. Now there's a little bit of maths involved in working out how to simulate up the y-axis, and that involves doing an integral on the intensity inside the region which is simulated. This boundary here, by the way, doesn't have to be a straight line. It can be any function you like. I mean, and varying that function is useful. So now the first approach, which is the one that was published in these papers, was to not worry too much about compensating for the fact that the short flows have been emitted, because that's obviously an error. But because the observation was only made at the final instant, it doesn't lead to a significant error. And so by collecting statistics only at the final moment, we can get satisfactory, well, unbiased statistics. Now, there's a problem with this. It means that there's a limit to the accuracy that can be achieved, and there's a couple of solutions to that. One of them is to collect statistics all the time. Well, not all the time, after a certain interval. In other words, we have a kind of warm-up and then we collect statistics. And in that case, we need to compensate for the fact that these short flows have been emitted. Now, because they're so short, they're actually going to operate like a background load. So it's common in some systems to simulate to replace them by a constant, by a change in the server rate, if you like. But a better technique is to add flows on the boundary, and that will still be efficient. It won't be difficult to simulate those, but it will be it'll be more consistent with the true model. One nice thing about this is that although we've still got a Poisson process here, we've now got a Poisson process where the intensity has some sort of finite measure, non-zero measure on that line, zero measure here, and it's also got non-zero measure in this area. So we've got a measure which doesn't have a density and is not discrete. And it's sort of sometimes difficult to motivate measure theory because you're always looking at situations where you'd either be better with a density or with, you know, a discrete model. But in this case, you can't get away with it. Measure theory is absolutely essential. Okay, now the concept of just having one observation. Now, by the way, the name snapshot comes from the fact that it was originally designed to have just one observation. So that's why the term snapshot. But that obviously limits the statistics. Now, what we could do is to use the methods which were described yesterday. And I have tried that, and I guess I ran out of energy. I mean, so in other words, we could use importance sampling to emphasize the tail, and that would give us improved observations, even although we were only making one observation. Another approach is to try and collect statistics continuously, and but that requires a great deal more care because our model is actually inherently biased. We have hardly any small flows and a lot of large flows. So we have to think about what to do, and the answer, I believe, is we need to collect statistics per flow size and then correct them. And that's basically the same, that's just importance sampling in a sense. We have a biased model. The model is deliberately emphasizing the large flows. So even although what I'm describing here looks quite sort of, you know, oddball in a sense, it's not like typical importance sampling. In a sense, I suspect with a little twist of thinking, it actually can be put in the framework of importance sampling in a more conventional way. Okay, so some conclusions. I sort of suspect I might have given myself a bit of spare time at the end. So the problem of simulation in which the paths are that we need to explore are too long to simulate has been tackled, And the solution that we've come up with is to simulate, is to have a different starting point for flows of different length. So, for example, in the simulation of the 20th century, we actually simulate also the 19th century, the 18th century, the 17th, back to whatever. But we only simulate the big events at that time. And then it's only at the start of the 20th century that we start simulating having lunch and going to the toilet. So that's the basic idea. And the mathematics of how to do that has been developed, and you can look that up in some of the papers that were mentioned there, which are all available from a website if you just do a Google search. And systems with fair queuing and with shortest job first and variations of other sort of oddball queue management strategies have been simulated. And the results do conform with analytical results as far as they've been tested. And the continuous collecting of statistics is under development. And I also would be interested in tackling the importance sampling approach to emphasise the heavy tails, the tails of the distributions. But that hasn't really been completed. Okay.
Could you say more about what statistics you're actually trying to compute here?
There's no inherent limitation on the statistics that can be collected. If it's only an observation, in other words, in the original snapshot, it was limited because it really could only be about the state of the system at a certain moment. So it wouldn't be possible to say things, to collect statistics about a duration. Even a duration would be out of bounds. But I guess it's things like the average delay before a flow is accepted into a network, in principle. But initially I was just looking at things like delay and loss for certain types of flows.
So you have some queuing discipline in mind here.
Well, yeah.
In the system?
Yeah, I mean, the classic model I'm looking at is say, the internet with flows. It's very widely accepted that it's much better to model the traffic in the internet by means of a flow model. I mean, we'll see a lot more about that on Thursday and Friday. But ignoring the flow nature of traffic in the internet is sort of a big mistake. So, and even the performance that we experience should really be measured in terms of flows. So, for example, when you access a web page or do anything, what you're interested in is how long does it take for my service request to be satisfied. And so your service request is well modeled by a flow. A flow in the broad sense is really a set of activities on that network which are so heavily correlated that it doesn't make sense to treat them as all independent. So there's a sort of, the way I'm using the term flow is in a sense an approximation of the fact that real traffic has a very complex correlation structure. And the best simple way to capture that is to say that we will say that these things in this flow here are totally correlated. They're all mixed together. But this flow is totally independent from every other flow. So that's the sort of models I've been looking at. So the statistics, the best statistics to collect are about flows. Because we expect a short flow and a medium-sized flow and a large flow to all have completely different experiences. In fact, they should. So, for example, if you're out and about in the world with your iPhone, you actually want to have a completely different charging regime when your son or daughter, decides to download a movie, because that's a large flow. Let alone have different statistics for it and different performance. What you want is lousy performance and low charging for such flows. And that's exactly what networks are sort of tending to provide, but they're a bit slow in doing it at the moment.
So is the rate taken into account here of the flows?
Good point. Yes, I'm looking at
Or you
two.
just
Well, there are two
assume-
extremes here. One of them is that we assume the flow has a fixed rate,
Yeah.
and in fact, in the extreme case, every flow has a fixed rate. But at the other extreme, we say, okay, the network will decide. We've got 10 flows at the moment. We'll give each one 1/10 of the service rate, and that's fair queuing. And in the internet, the big model, the one which is sometimes referred to as if it's really the way the internet works, is fair queuing, also known as processor sharing. But you know, it's not a perfect approximation by any means. Now, in these papers, I've been dealing with both of those cases, or you know, more than two cases really. But at one extremity, I've been talking about. There are some of those papers which refer to the model where each flow has a fixed rate. The way I look at it, in fact, there are two places in the internet which are completely different. One of them is in the core. In the core network, basically the flows don't see the network. There's no congestion, and so they behave as if they have a fixed rate. From that, just looking at it locally. But in the access network, it's quite different. In the access network, basically all the flows are competing with each other, and we have this processor sharing sort of discipline is pretty much what's happening. In other words, there's a bottleneck there, and at that bottleneck, the flows are fighting it out and getting roughly an equal share, which may, in some cases, be a bad strategy. But it's actually not too bad either. I mean, it's not as bad as a really bad strategy. But
So in this two-dimensional diagram, were the heights supposed to be durations or
the size,
or the load?
size of flow,
Size of
size of flow, yeah. So that's why we can talk about it being a Poisson process, because there's nothing to do with network behavior. The size is something which is decided at the point of origin. You know, I want to download, Star Wars, or I want to do some internet banking. That's the decision. That tells you what the size of the flow is. And then, so in that diagram, we have complete knowledge of the statistics, because we decide on what the statistics are going to be. It doesn't depend on what other flows are in the system. So that's quite rigorous.
Any other question?